Hello, thank you for the introduction. I will talk about our work in which we propose two new versions of existing encryption schemes, the RQCE and the LRPC protocol, which relies on rank-based cryptography. So I will begin by a little contextualization. So you certainly know this usual problem. You have a matrix, a non-normed vector X, and a syndrome. You have to retrieve the vector X. If you have absolutely no constraint, it's an easy problem. You have only to solve a linear system of equations. So we will add a constraint on X. If we limit the Hamming weight, it's a well-known code-based cryptography. If we limit the Euclidean distance, it relies on lattice problems. And we will interested in the last case, the long distance, which relies in rank-based cryptography. So the long distance makes sense in an extension field. So we are in a finite field FQM. The support of a vector is the coordinates is the FQ linear space spanned by its coordinates. And the weight of the vector is the dimension of its support. And like in Hamming metric, we can define a linear code with a generator matrix whose lines generates the code, or the parity check matrix whose rows, generates the orthogonal of the code. So we can similarly define some difficult problems. So the rank decoding problem, so like in Hamming metric, the only difference is that we have to find an error of a small rank. And we have its equivalent problem, the rank single-volume decoding problem, in which is given the parity check matrix and the syndrome. So I will begin to introduce the original RQC scheme. So to do that, I will present you what is a Gaby-Dolan code. So it's the analog of Reed-Solomon codes in rank metric. So you have some evaluation points, but rather than take standard polynomials, you take linears the polynomials. It's polynomials whose the only non-zero coefficients are associated to powers of Q monomials. And like Reed-Solomon codes, we have an efficient decoding algorithm which allows to achieve the same decoding capacity. So when you want to use code word in a cryptographic schemes, there exist two possibilities. The first possibility is to mask the code that you use. The problem and keep the code in the secret key. The problem is the Gaby-Dolan code is a very structured code, so it's very vulnerable against structural attacks. So for the RQC code, there exists a second possibility. Rather than hide the code, we hide the code word. So we see that J, the generator matrix of the public key is in the public key. It's in the public data, and we use it to encrypt the scheme and to decrypt the you can obtain the noisy code word thanks to the coefficients in the secret key. Now I will present the LRPC protocol. So I will present an LRPC code. An LRPC code is a few structured code. It's a code for which there exists a parity check matrix whose coefficients span a vectorial space of small dimension. And the advantage is there exists a very efficient decoding algorithm. It's the rank support recovery algorithm. So what we must do? So we have the syndrome and the parity check matrix. So we have the E is the support of the error that we want to retrieve, but we know F the support of the parity check matrix and the theoretical syndrome space. So the product space of the vectorial spaces E and F. And by computing the set E by this formula, we can retrieve the error. The problem is there is a main drawback because exist two possibilities of failure. The first problem is we don't have the equality for E. We can just prove an inclusion. And the second problem is, and a problem which happens more oftenly with a higher probability, is that the syndrome doesn't span the whole theoretical product space. And it especially happens when the product space is of a high rank, of high dimension. But the advantage is RFPC code, since they are less structured, are more easy to hide. So in this case, X and Y allows to define a LRPC code, so they can be seen as polynomials, and thanks to idle codes, we can define a code. That is the original scheme of LRPC, which is historically a K encapsulation mechanism. So now I will present two existing optimizations that allow to improve these protocols. The first is a multi-syndrome approach. The concept is rather than give a non-Lie syndrome, you give several syndromes associated to errors which have the same support. So it's a wrong support learning problem. So of course, since you have more information, it's easier to decode a code word. And another way to improve the decoding capacity of code is the introduction of augmented Gabby-Dollin code. So an augmented Gabby-Dollin code is like a Gabby-Dollin code, but you add, you concatenate at the right some zeros. So what happened when you add the error? In the last coefficients, we will immediately retrieve some coefficients which belongs to the error. And we insist it's especially efficient in rank metric because, as I said, we have a more global notion of error. It would be absolutely no pertinence in naming metric, since in the first coefficients, you would have absolutely no information on the support. And it allows to improve the decoding capacity of the code. And the another optimization which has been recently introduced is a blockwise error. So the block error, you split your vector in several blocks, and you ask to the support of each block doesn't intersect with another. Maybe you know the sum-rank metric in which we split you split your vector in several blocks. And the sum rank weight is equal to the sum of all the weights of each block. And the homogeneous error can be seen as an intermediate between a classical rank metric and sum rank metric, because it's the only case where these two metrics coincide exactly. So what is the advantage of block errors? In the same article, the block LRPC code has been introduced. It's like block errors, but you can cut your parity check matrix in several blocks, whose the support of each block doesn't intersect with the other. So what happened if you compute a syndrome with a block error? You will obtain a syndrome with smaller spaces. The sum of you obtain the sum of several syndromes which has a smaller product space. I will give a concrete example. If you have an RPC code of 2 blocks of size n, and if you have a block error of 2 blocks of dimension r of weight r divided by 2, you have an error of global weight r. And if you have your LRPC code, which has 2 blocks of weight divided by 2, it's an LRPC code of dual weights d. So if we consider this like 2 errors, the syndrome is of weights rd divided by 2. So we divide by 2 the theoretical syndrome space, which allows to clearly decrease the decoding failure rates of the rank syndrome recovery algorithm. So we have seen two kinds of optimizations. The two first, which allow to improve the decoding capacity of the codes, and the last, the block errors, which allow to reduce the weight of the considered vectors. In our work, we show that we can combine these two optimizations. And we will propose new versions of RQC and LRPC schemes. So it's our new version of RQC of the RQC scheme. The only difference relies on X and Y are a block can be seen as an only vector of two blocks. And in R1, R2, and E, we sample N1 N1 errors, which has all the same weights. Why it is an advantage? So the weight of the error to decode is this one. So if we assume that all these values are equal to R, with blockwise errors, the error to correct would have weight 2R squared plus R. And if we consider this as a standard errors, the error to correct would have weight 6R squared, which allows to better increase the parameters of the scheme. And we can do the same thing for the LRPC protocol. So the LRPC matrix is still in the secret key, and like in the previous case, X and Y can be seen as an only vector of two blocks of dimension D1 and D2, which allows to define the two LRPC matrix code. And for the same reasons that allow to clearly reduce the parameters of the schemes. So I will now present you our second contribution. I will present an attack on the two LRPC code. So if you have a two LRPC probability check matrix of a code, we want to retrieve the structure of the code from the generator matrix J by finding a word of rank R1, R2 in the orthogonal matrix. If you obtain this word, so you obtain the support of this word and the support of the LRPC matrix. So the advantage is since the coefficients of the matrix span vector space of small dimension, we can put several coefficients to 0 with overwhelming probability. So we can assert that there exists with high probability word with 0 coefficients whose the first coordinate are zeros. So the only thing we have to do is to find this word, and if we find this word, we are able to retrieve the support of the blocks. So we propose a cryptanalysis with this attack of the parameters given in the article which introduced the blockwise errors and the block LRPC codes. We see that with this attack, we are clearly under the classical levels of security. For example, for 128 bits of security, with our attack, we break the parameters. So we can see with our contributions, we can achieve, when we do the sum of the public key and the ciphertext, we can achieve 1,400 kilobytes approximately. We can see the history of several propositions for the I2C protocols, and the progressive amelioration of parameters. And in the case of LRPC block, we achieve a size of 1,700 kilobytes for 128 bits of security. If we compare with other known schemes, for 128 bits of security, we do better than lattices. Yeah, thank you for your attention.
Thank you. We have time for one question.
Thank you for your talk. I just have some question about the LRPC code and the LDPC code. So LRPC is in rank metric and LDPC is in Hamming metric. But when we use LDPC code for encryption,
yeah,
there is a requirement on the density, right? It should be MDPC. But why we can use the low rank parity check codes in the rank metric?
Sorry, I'm not sure to understand your question.
I mean, in Hamming metric, we should maybe increase the density, but in the rank metric, why don't we? I mean, we don't need to increase the rank, right? We can only use the low rank. That's the difference. Okay. Well, why do we have such difference?
Why we use rank LRPC code rather than LDPC codes? It's
Yeah.
oh, okay. The first thing is in a rank metric we achieve better parameters than in Hamming metric, so it's the main reason. And the other reason is that there exists no notion of block in Hamming metric. I don't know if I answered to your question, but
maybe we can talk offline. Okay, thank you.
Okay, let's talk. Yeah, thank Adrien again.